First part of our chapter has been, dealing with covalent compounds, which is electron sharing. We notice that these things, once they share the electrons, have low melting temperatures. Some of them dissolve easily in water, and of course some of them conduct electricity, but others do not. We're now going to look at ionic bonds, which is the transfer of electrons from one atom to another. And these usually have high melting temperatures. A lot of them do conduct electricity, but not all, and most are soluble in water, but not all. So there are some similarities between the two types of compounds. But how do we diagram them? Well, let's take a look at sodium chloride. We know that one sodium reacts with one chlorine. We know that because in this group here, this is group 1, that's where sodium is, it's a positive 1 charge. And chlorine's over here has a negative 1 charge. But why does it work like this? Plus 1 to minus 1. They cancel out, therefore there's our compound. Let's take a look. Sodium, in this column over here, has 1 dot. Chlorine over here has 7 dots. Now, sodium is a metal, and it likes to give up electrons. Chlorine is non-metal and likes to receive electrons. So instead of deciding to share electrons, sodium says, well, why don't I just give you, chlorine, my electron? So I'm going to draw an arrow over there. In doing so, sodium has lost its electron, therefore it becomes plus 1 in charge. And chlorine becomes the chloride ion and becomes negative 1 in charge. Now that's called diagramming, or showing how the ionic bond occurs between sodium and chlorine. One electron given from sodium is received by chloride. But what does it really actually look like? In 3 dimensions, it's an ionic crystal. What holds the sodium and chlorine together are the opposite charges. Opposite charges attract. And those bonds are usually very, very hard to break, and that's why their melting temperatures are so high. Here's a crystal lattice structure of sodium chloride showing alternating red, which is the sodium, and green, which is the negative. And it just makes a 3-dimensional structure. And you're probably all familiar with what sodium chloride or table salt looks like. Let's try a couple others. Next one is magnesium chloride. We see magnesium is a plus 2. It's in the second group here, plus 2 group. And chlorine still in the group 17. Down here are the halogens as minus 1. And then to make this compound's name become symbols, we would crisscross charges. But how does it work? When we look at magnesium, magnesium is in group 2 and has 2 dots. Chlorine still has 7 dots, but I'm going to write 2 chlorines. I guess I'll write the other one here. So again, we're diagramming how this should come together. So magnesium says, well, I've got 2 dots, therefore I can share 1 dot with each chlorine. So we're going to give 1 electron over to this chlorine to make it the chloride ion. Notice how it changes its name when the electron transfer occurs. And we'll give this electron over here for this chlorine atom to make it a chloride ion. Now, since magnesium has lost 2 electrons, that's why it's the positive 2 charge. And each chlorine still gains 1 electron, and each one's negative 1 charge. You can think of it a couple ways. Negative 1 plus a negative 1 equals a negative 2, plus the 2 here equals 0. So the sum of all charges in a compound should equal 0. But you can also think of it this way. Magnesium has 2 electrons to give up, and there are 2 chlorines there to receive them. And that's how we diagram it. Now, of course, this will make a 3-dimensional crystal lattice structure as well, but I'm not going to go through all of the crystal structures today. But just realize there will be some kind of crystal of alternating positive magnesiums and negative chlorines as they're all attracted to each other to make the crystal. Let's do one last compound. Aluminum oxide. Aluminum being plus 3, oxygen's minus 2. We, of course, would crisscross charges. The 2 comes down here, the 3 comes down here. Where do we get those charges from? Well, aluminum is in the plus 3 column, and oxygen is in the minus 2 column. We now need to draw 2 aluminums. But how many electrons does each one have? Well, those are the P1 columns here, and the P1 column right here all has 3 electrons. First 2 are paired, and 1 by itself. First 2 is paired, and 1 by itself. So then there are 6 electrons available to be transferred over, because aluminum's a metal, and will transfer its electrons over. Let's draw 3 oxygens. Oxygen is in the 6 electron column here, being in the P4 column. So we know there are 2 dots paired, 2 dots paired, and 1 by itself. I'll draw another one. I'll draw it here. 2 dots that are paired, 2 dots that are paired, 1 by itself, 1 by itself. And finally, 2 dots paired, 2 dots that are paired, 1 by itself, 1 by itself. Okay, now we will complete the outer level for oxygen by delivering electrons to it. I'll try to draw this so it's clear. So let's say this one electron goes here. Okay, and this electron here goes around here to this position. Now this electron goes here. And this electron goes here. Now we have 2 electrons left. And we'll draw this one all the way to there. And again, it really doesn't matter which electron goes where. We're just showing that there would be this kind of electron transfer. Aluminum has 6 total electrons to give up between the 2 of them, and 2 electrons go to each atom. We now have a +3 for the aluminum because it lost 3 electrons. Each oxygen gains a -2 charge because each gains 2 electrons. So the end goal is to give away whatever electrons the metal has and then give those to complete the outer level of the atoms receiving. Because each oxygen atom, once it receives the electrons, has 8 electrons. And they are -2 in charge. And that's how we diagram it. And that's our goal. Complete up the outer level for the nonmetal while giving away the electrons from the metal. And that's how ionic bonds work.